Hello, and in this video, in the start of the second chapter of Further Mechanics, we're going to be starting off by looking at something called work. Okay, and actually, before we do start, something to note for this chapter, we're going to be needing some stuff from normal maths on the mechanics side, even from year 13. So that'll be particularly relevant if perhaps you're doing this in year 12. Some people do further maths year 12. So what I will do in this video is, when relevant, I will go over very quickly just the stuff you need to know to approach this chapter. Okay, just the essentials. Okay, but even if you learnt it, it'll be a recap. Okay, so we'll look, so that's something to note. There is some prior knowledge. Okay, right, so work. So as you can see, I've got these two pictures on here. And so the idea of work, you can kind of think of it as a physical work, or working out, or movement, something like that, right? And the idea of work, you can see with these two pictures, is we've got this, we've got a person that's pushing something forward, right? So whether it's pushing a boulder up a hill or pushing a crate, okay? Those are examples of work done. So the idea of work is, work tells us the energy we use to push an object forward. Okay, so you can imagine with the top example, the person pushing a heavy boulder up a hill is going to need a lot of work to move it forward. Okay, so they're going to need to use a lot of force within themselves to push it forward, right? Compared to the second example here, you can imagine it's going to be easier to move the crate forward, so less work is needed. So in other words, less energy the person needs to move it forward. Okay, so I'll summarize here. Work essentially tells us the energy needed to move an object forward, right? Okay, and so we're going to need to come up with some sort of formula. Well, obviously there's going to be two ingredients. Well, the first bit is obviously force, right? If an object is heavier, we're going to need more physical force to push it forward, but also we need to account for how long we're doing it. For example, say if we push the boulder up here for 10 seconds, compare that to, say, a minute. Well, obviously we're going to need a lot more energy to move it in a minute if we keep doing it for a minute compared to 10 seconds. So actually we can say that as a formula, we can say that the work is going to be equal to the force times the distance moved from the object. Okay, and so that's the key formula we're going to be working with. Okay, now as for units, well, force is going to be in newtons, distance in meters. So for the units for work, then, well, you could deduce it's going to be newton meters if you literally multiply the units. But as I hinted here, it actually is involves energy, and it turns out, if you are quite clever with using other formulas, that actually we can also say the units are going to be in joules. Okay, and that's the common unit we use. So work is actually a form of energy. It's the energy we put onto an object to move it forward. Okay, and so that's essentially it. Okay, now we're going to be looking at our first set of examples. However, as I hinted, there is some prior knowledge we need before we step into this. So what we're going to look at first here. Okay, well, I've got a car on the on my screen here. So first, what I'm going to do is we need to just look at the actual forces acting on a car. Let's say the car is obviously moving forward. Well, firstly, you can see this force here. Now, if the car is moving forward, that means there's a driving force that moves it forward, okay? Driving force essentially means a forward force. So it's the force that literally moves you forward, okay? Now, again, as you can imagine, if you're on a road like this, there's then going to be friction that opposes it, okay? Or more generally, a resistance, okay? So so you can imagine the force is trying to stop a car moving forward, friction on the road, but also perhaps air resistance as well, right? So there we are. So those are what we call the horizontal forces. So that's the right and the left force, okay? So those are those forces. Now, actually, as well, you'd be aware that everything has a gravity that tries to pull it forward, right? Every object on the Earth has its gravity pulling it down. That is the weight, okay? The force that pulls you downwards due to gravity is your weight, okay? Now, then you can imagine, well, you're just going to sink through the road. So what keeps you up on the road? Okay, what stops the weight? And that is called a reaction force. Okay, so these are the four main forces we're going to be using extensively in this section here. So that's the forces. Hopefully happy with that. But of course, we need to be more mathematical. And so there's a bunch of formulas we need to know. The first one being that the force, the friction force, I'll do it over here. So key formulas. Friction is actually equal to this mu, this letter mu, this funny u, times the reaction, okay? Or more simply, F equals mu R, okay? So what this is saying is friction is a multiple of a reaction. Now, now more specifically, this mu is what we call the coefficient of friction, okay? I'll make a note of it here. So what mu, coefficient of friction, well, it's usually between 0 and 1, okay? So it's kind of like probability. So mu basically tells me how sort of slippery the surface is, so how slippery the road is, right? So if mu is closer to 0, that means it's very slippery, so there's barely any friction, okay? But if mu is closer to 1, then that tells me it's very sort of sticky. The car will stick to the road essentially, a lot of friction. So you can imagine if it mu's at 0, it's going to be icy, very slippy. But then if it's 1, it's going to be hot and sticky, okay? So actually that's a formula we can use to link the friction to the reaction, okay? The second formula is actually to do with the weight, okay? So we can actually say that weight is equal to the mass of the object, so the mass of the car, times g. Now g is just a number, it's a constant number like pi and stuff like that. Now g, we usually say g is 9.8, okay? So we can actually say that the weight, so we can say that W is equal to mass times 9.8 usually, okay? So that's, so there we are. So we can compute the weight using this formula as well. Now the last formula is going to be force equals mass times acceleration. Okay, so if the car in this example is moving forward, then there's going to be an acceleration there. Okay, so there we are. So acceleration tells me if something is speeding up or slowing down, by the way. Okay, now again, we can summarize that as F equals ma. Okay, so these are the three formulas you need to know before we go into this. Okay, now as a quick sort of numerical example to demonstrate this, let's say I have a car. I'll do it down here. 50 kilogram, 500 kilograms. Okay. I have my my weight W. So my weight. I have a reaction force. I have my friction. And I have my driving force. Okay. And also the acceleration in this case, I'm going to say is 10 meters per second squared. So that's the setup, right? And the idea is now I want to find all forces. Okay. Using these three formulas that I've boxed here. Okay. So firstly, I can compute the weight. Okay. So firstly, the weight. Well, as I said, that the weight, that's going to be mass times G. So G is 9.8. Okay, so well, the mass is 500, right? So that means the weight is 500 times 9.8. And so that will be, if we work out that, 4,900. Okay, and that being newtons because it's a force. So that means we can say that the weight now is 4,900. Hopefully we'll be there. So weight is mass times 9.8. Okay. Okay, so that's my weight then. Now I'm going to find the reaction force. I'm going to do that by now looking at this formula. Force is mass times acceleration, or F equals ma. Okay, well, what exactly do I mean by force? Because there's four of them here, right? Well, so what we can do is actually look at two different sort of directions, okay? We can look horizontally, so the right and the left force, then my driving force to the right and my friction to the left, or we could look up and down, so vertically, which is my reaction and my weight force, okay? So what I'm going to first look at is up and down. So what I'm going to say is R, so resolve up and down like this, okay? So I'm going to look at my upwards and downwards force, right? Well, firstly, upwards is the reaction. Take away the downwards force, so the opposite force, which is 4,900. As we just worked out, that's the weight. That's going to equal mass times acceleration. Okay. Okay, right. Now, the math. So if I write this out again, reaction minus 4,900. Well, the mass is 500. And the acceleration now. And now, because we're looking vertically, you might think, well, I said the acceleration was 10, but look at the direction. The acceleration is horizontal. It's moving to the right. Okay. But this is different. We're looking at the up and down direction, the vertical direction. There is no acceleration upwards. Okay, 0. Okay, so that means vertically there is no vertical acceleration, because this again is a horizontal acceleration. Okay, it's moving right and left, so that means the vertical acceleration is 0. Okay, so that's the idea. We can split up to horizontally and vertically. Okay, but there's no acceleration vertically, so actually it turns out this all equals 0. Therefore, simply my reaction is also 4,900 newtons. So I can add that on. Right, what's next? I'm now going to find my friction force. Now that I'm going to use the final formula we haven't used. That's going to be the my friction is mu, so my coefficient of friction times reaction, or F equals mu r. I've not told you what it is. I'm going to say that mu is 0.5. So again, the coefficient of friction that tells me how slippery the road is 0.5. So again, friction is mu. Actually, what I'm going to friction is mu times the reaction, and I'm going to box. I'm going to box my solutions to make it clear to separate things. Okay, so that's my weight. That's my reaction. Okay, now looking at friction. So friction is mu times reaction, but I know my reaction, it's 4,900, and that mu is 0.5. So my friction is going to be 0.5 times 4,900. And so that would get me 2,450 newtons, and that is my friction. Okay. I can add that on then, my friction of 2,450. Right, the final force we need to find is the driving force, so the forward force, right? So to do that, well, we've looked at the vertical, the up and down forces. Now we need to look at the right and left forces, so the horizontal ones. So again, what I'm going to do now is say resolve right and left like this. Okay, so my right force is again my driving force. Okay, then I'm going to take away the opposite, so that's going to be my friction force in the opposite direction, 2,450. And so that's going to equal mass times acceleration, right? MA. Well, my mass is 500. Now the acceleration is going to be 10 here, because the acceleration is 10. That's horizontally, but we are looking at the horizontal forces, right? So actually the horizontal acceleration, which is what we want here. So again, this is horizontal, so right and left. And then the one we looked at previously was vertical, so up and down. So the horizontal acceleration is indeed 10. And so therefore we simplify this, the driving force, take away 2,450 equals 5,000. Okay. So therefore we can then work out the driving force by adding this 2,450 on to be 7,450 newtons. And there we are, that is my final force. Okay, I can add that on. Okay, so that is just a breakdown of the key things you need to know before we go into this. So these 3 formulas here, now hopefully this has shown you how we can use the formulas there. Okay, but again, hopefully you may have seen this already in normal maths, but there we are, we will be using these techniques. Okay, right, now we're going to look at what we do need to know. What we were supposed to be looking at work. Okay, so we've got this first question here. I'm told a box is pulled 7 meters across a horizontal floor by horizontal force of 15 newtons. Calculate the work done by the force. Okay, well, work, as we've seen at the start, the work is the force times the distance moved, right? Well, actually, we want to find the work. We know the force is 15, and actually the distance is 7 meters. Well, actually, that's quite nice. We just use the formula to get the work to be 105 joules there. Okay, or Newton meters, right? Whatever units you prefer, but that's the number. Okay, 105 there for the work. Okay. Okay, so we've got this question here. So we're told a packing case is pulled across a horizontal floor by a horizontal rope. The case moves at a constant speed and there's a constant resistance to motion of R newtons. When the case has moved a distance of 12 meters, the work done is 96 joules. Calculate the magnitude, so the number of the size of the resistance. Okay, right, so this is a bit more wordy and a bit more weirder than the last example. So what we need to get into the habit of, if we haven't already, is to start to draw the situation out, because it will really help visualize the equations we need to do. Okay, so if we look at the first example very quickly, if we were to draw it out, okay, so a box is pulled 7 meters across a horizontal floor. So we've got a floor like this, okay? That's a horizontal floor. So we have a box, okay? And it's being pulled by a force of 15. So it's been pulled like this, the force 15. So the, and then the distance is 7 meters. So that's the situation there, okay? It might be quite simple, but that is the diagram there. Now, if we were to draw the diagram here then, so again, I've got this packing case. So it's being pulled again on the floor. So again, we have our floor. This is my packing case. Again, I'm just going to draw a simple rectangle, a little box. No need to overcomplicate it. This is my case. And it's being pulled by a rope. Okay, so it's going to be pulled forward, right, again. So what we're told is the case moves at a constant speed and there's a constant resistance to motion, okay? So the resistance to motion, the case is moving forward, right? Resistance, or sort of friction, is going to then go the other way like this. And I'm told that force is R, okay? I'm told that the case has moved a distance of 12. The work done is 96. Okay, and so therefore there would be a driving force moving forward, right? The forward force is a driving force, okay? Or you might spot it's a rope, so specifically it's a tension force. But there we are. That's the setup here. Okay, hopefully happy with that. There's a forward force that's pulling the case, and a resistance, so it's opposite to the movement. Okay, so it works backwards. Okay, I am told the case has moved a distance of 12 and the work done is 96. So we're told the work, okay? So again, if we use the work formula, work is force times distance. Well, what force is it referring to here? So the work done is the force moving it forward, right? So it's going to be the work done for this force D, the driving force. So if we use the formula then, that's going to be equal to D times the distance, which I'm told is 12 meters, okay? Well, I also know what the work is. It's 96. So actually, we just get this equation here. 96 is D times 12. Therefore, D, if I divide by 12, I get 8. So actually, my forward force is 8 newtons there. Okay. But they want me to find the resistance force R. Okay, so what do we do here? Okay, we don't know really anything about R, right? Now there's very specific detail here. they mention it's travelling at a constant speed. Okay, obviously we don't know what the speed is, but that doesn't matter. What you do need to know is constant speed. Whenever you see that term, specifically if it's constant, that means there's no acceleration. Okay, just something you need to know, which makes sense because acceleration is, it tells us if speed is changing. If the speed isn't changing, then there's no acceleration. But there we are. So that means we can mark it on as saying acceleration, right? Like this is 0. And that's going to be meters per second squared. Okay, we write it like this. Okay. So that means then, well, what else can we do? We can actually then resort to using F equals ma, forces mass times acceleration, right? Now, specifically, we're going to be looking horizontally, so right and left. Okay, so my forwards force is 8. Take away from the backwards force, which is R. That's going to equal the mass, and actually, we're not told the mass. We don't need it though, because mass times acceleration is 0. So actually it all just boils down to 0 anyway. Therefore, we can deduce R is 8. And that is my answer there.